Okay, this is still more introduction to basic probability, and we are going to be focusing on what appear to be dependent events and the complement. So once again, probabilities, comparing the ratio of what you want to happen to all the possible outcomes that could happen. Remember, all of our probabilities must be between 0 and 1 inclusive. There's no probabilities greater than 1, and there are no negative probabilities. So dependent events, a group of simple events where one outcome does impact another. So consider this. We have a bag containing 3 A's and 5 B's. What's the probability of drawing 2 A's at the same time? Technically, this is a dependent event, all right? Because you can't do that. So what we have to imagine is breaking it down into 2 independent events. So let's do the probability of drawing 1A. Well, the probability of drawing the first A would be, okay, 3 out of 8. Well, that's easy enough. But we still have the problem of the second A. Well, now in the second A, it's like we went back to the bag and we only have 7 total letters and 2 of them are A's. So it's essentially we had a bag with 8 letters and then a bag with 7 letters. But basically you're having to draw 2 separate times. So we've made them into 2 independent events. Although it was dependent, this changed the probability, but because we have now changed the probability, we can multiply them. Because remember, we can only use this multiplication rule, probability of A and B equals the probability of A times B if the events are independent. Well, since we drew the first one, definitely independent, not impacted. The second one was impacted, but we made the adjustment to the probability. And since we made the adjustment, we can go ahead and multiply it. So what's the probability of drawing a B on the first draw and then drawing an A without replacement? Once again, this is a dependent event. So we're going to start off with our first probability of drawing a B, which is 5 out of the 8. But now that I've drawn one of them, I have 3 A's still left, and the probability of drawing from that second bag is independent. So I can multiply 5 8s times 3 7s because there's only 7 letters left. What's the probability of drawing 3 A's in a row without replacement? So in this case, I'm going to need 3 blanks. Blank, blank, blank. Probability of the first one would be 3 out of 8. The probability of the second one is 2 out of 7. The probability of the third one is 1 out of 6. And so because I made the adjustment, I can multiply them. Technically, it wasn't independent to begin with, but I made an adjustment. And because we made the adjustment, they are now independent events. So with 3 A's, we ended up having 3 8s times 2 7s times 1 6. What if it asked for 4 A's in a row without replacement? Well, I crossed off the first one at 3 8s, the second at 2 7s, the third at 1 6, and then I have 0. So I'm multiplying by 0. So there's no way we could have 4 A's without replacement here. All right. That wasn't one of the questions, but that was for free. What is the probability of drawing 2 A's in a row and then drawing a B without replacement? Well, once again, we're doing 3 things. So we need 3 blanks. The first A would be 3 8s. The second A would be 2 7s. And now we want a B, and we have 5 B's out of 6 letters. All right, our next question. What is the probability of drawing an A, replacing the letter, and then drawing a B? So we have 3 out of 8. We replaced it, and now we have 5 out of 8. And finally, what's the probability of drawing a B without replacement and then drawing a letter? Well, once a letter A. In this case, it'd be 5 8s times 3 8s, but regardless, we're going to get the same response because we're just multiplying. And they were actually truly independent events, and the probabilities didn't change. So if you have a dependent event, as long as you can make it into a situation where it's an independent event, then you can go ahead and multiply them. And that's what we did up here. Once again, we drew an A, and then we acted like we had a bag that no longer had 8 letters, 3 of which were A's. We had a bag that had 3, we started off with 3 A's out of 8 letters. We had a second bag that had 2 A's out of 7 letters. It's like, oh, drawing from one bag and drawing from the second bag are independent. So we could go ahead and multiply them. So if you can force it into that situation, you can move on. The complement is the probability that an event will not occur. All right. And generally speaking, and say, what's the probability of not this? We've already seen some of that. We've said, what was the probability of not red or not tails? So, and we often express it as the probability of a complement, which means the probability of not A. So what's the probability of not rolling a 3 on a 6-sided die? Well, we have 1, 2, 3, 4, 5, 6. So the probability of a 3 equals 1 out of 6. And by the way, that P just stands for probability. So the probability of not 3 would be 1 minus 1/6, which is just 5, 6. And you're like, well, that makes sense because there'd be 5 other numbers. What's the probability of not drawing an ace from a deck of cards? Well, to know that, you have to know how many aces there are in a deck of cards. So first off, a deck of cards has 52 cards, 4 of which are aces. So the probability of an ace would be 4 out of 52. So not an ace would be 1 minus that. So the probability of A is 4 out of 52, so not would be 1 minus. If I draw 3 cards without replacement, what's the probability that none are aces? Well, I need 3 blanks. The probability the first is not an ace is 48 out of 52. Now I have 47 cards that are not aces out of a total of 51 cards. And then the next one, I have 46 cards that are not aces out of 50 total cards. Because remember, in all cases, there were 4 aces because we didn't draw any of them. Finally, the at least questions. With at least questions, you always need to work with the complement, and these are super, super important. We've already looked at this problem, but we'll look at it again. If a student guesses on 5 questions, multiple choice with 4 answer choices, and let's just say those answer choices were A, B, C, and D, and previously we said A was correct and these were wrong. What is the probability the student gets at least 1 wrong? All right, so that means we could get 0 wrong, 1 wrong, 2 wrong, 3 wrong, 4 wrong, or 5 wrong because there's 5 questions. We want at least, so we're looking at that. So I could do 1 minus the probability of 0, which would be none wrong. Well, the probability of none wrong would mean that I got them all correct. And the probability of correct is 0.25, 1 minus 0.25 to the 5th power. So the probability of getting 1 wrong on it where you just guessed, pretty high, almost 100%. So, new problem. A machine has 4 components. So components with the probability the components do not fail during the year are 0.97, 0.99, and 0.96. If any component fails, basically they're saying if any one component fails, the machine fails. If none of the components fail, the machine works. What's the probability that it fails? We are going to assume that the components fail independently. May not be a good assumption, but we're going to need to do that so that we can do this problem. Most of the time, we'll be more explicit than that and tell you that they fail or don't fail independently. So let's look at this real quickly. This is the probability the machine works. This is the probability that component works. This is the probability that component works. And this is the probability that component works. And if I were to multiply all of these components together, all these probabilities together, that would give me the probability the machine worked. All right. But we didn't want it to work. We wanted it to fail. So this would be the probability of all four working. So remember, we could have 0 components fail, 1 component fail, 2 components fail, 3 components fail, or 4 components fail. If all of them work, the machine works. So the probability of 0 failing makes the machine work. 1 minus the probability of no failing equals the probability that a 1 does. So I just say 1 minus that probability. Probability the machine works all year long, 90%. Probability of having it fail is 1 minus that, which is almost 10% or 9.6%. Please remember, probabilities have to sum up to 1. So this is the probability the machine works plus the probability the machine fails. And it sums up to 100%. All right, thank you.